Also, the other thing which I was planning to remind you today of that is that uh, we decided to enter into the math modeling challenge competition. So far, Rose has enrolled into the competition with two other students from my advanced function class. The competition, Rose, is gonna be, we enter into the competition on on May the 7th next week, and we have 5 days to finish that. You can collaborate with me, with the other students. I help you for the challenge. But today, if Gloria and Philip also, they can enter into the team to be a part of the competition. But however, today I just want to share the screen with you. I'm gonna, oh, by the way, Rose, I have created a folder into the course main page. This is called Math Modeling Challenge. There are two PDF resources there. Please just take a look into that, okay?
Okay.
And by all the things which we have done so far with the bacteria mitosis modeling, with the Hodgkin-Huxley model which you have done, the challenge which you're just going to have is going to be much easier. But now, tonight, every day, we watch a 3 minutes video. It's a kind of a motivation to what is a modeling challenge? What is that? I'm just going to share my screen with you. Today and tomorrow, we start our sessions by that. We watch a 3 minutes video, which is about the math modeling and why that is good for. Are you ready for it today?
Yes.
Awesome. Then I'm just going to share my screen. Let me first of all find that link. And also tomorrow we see the second part of it. And let me share my screen with you all. Okay, let me share the screen. Okay, guys, can you see my screen?
Yes.
Yes. And let me know if you can also hear the sound. Can you hear a sound?
Yes.
Awesome. Then guys, please watch that for 3 minutes. Then when we are done, we have some kind of, I should say, some stuff to share to tell me what you think of it. What is your feedback? And Rose, you please also listen very carefully because it's talking about what is the main strategy of doing a model with the math. Okay, Rose?
Okay.
Thank you.
The world around us is filled with important unanswered questions. Try this one for size. What is all that math we learn in high school good for anyway? As it turns out, all math, from arithmetic through calculus and beyond, can tell us a lot. For instance, which recycling program is best for my city? How will a new flu outbreak affect the US? Or even, which roller coaster is the most thrilling? These are real-world scenarios for which math modeling can provide understanding or solutions. Modeling is a process that uses math to represent, analyze, make predictions, or otherwise provide insight into real-world phenomena.
When you're analyzing and looking at the models and everything, you get to see how these numbers are used and how you can actually apply the math that you learned.
In my opinion, anything in our life can be modeled mathematically, so we can always find a pattern in our life.
Here's how it works. Start with a basic definition of your problem.
If you define the problem, research will become a lot easier, and you'll actually understand what you're doing rather than just mindlessly researching and having so much research but not really knowing how to apply that research.
To simplify the scope of the problem, you'll need to make a few assumptions.
If you make assumptions, you can get rid of some extraneous and insignificant factors, so your model really only considers the most important variables.
Next, define your variables.
If you're trying to make a mathematical model, you are trying to create an equation of some sort that incorporates certain variables. By defining those variables, by figuring out what those variables are, especially early on, you know what you're looking for,
Now it's time to use the math that you know to build a model. This is where you'll first see your solutions.
We just used algebra the entire time. So we didn't have to go into calculus or differential and integral equations. We just make a couple of assumptions so that you can use easy algebra instead of taking some really long, complicated method.
Next, you'll analyze your model to make sure it works. Ask yourself, what can I learn from my model? Does it answer the original question? Does the answer make sense?
The analysis is just essentially looking at your data and showing how your data correlates with what the hypothesis that you're giving.
Finally, you'll report your results.
Model is more than just math. It's what assumptions we made, how we came up with those assumptions, and the justifications is extremely important.
Math modeling can help us answer big, messy questions about things like recycling options, spread of disease, and even the thrill factor of roller coasters. So now, instead of asking, what is all this math good for? The question becomes, what can't we figure out with math? For more information on the math modeling process, visit m3challenge.siam.org.
Okay, brilliant stuff. Guys, this quality of the sound, how was it? Was it good?
Yes.
Awesome. What do you think of that? Rose, I start from you because you are going to be part of that team then. Did you see that? They were talking that there are 3 stages of the modeling. And one stage is that to make many assumptions in order to make the problem so much simplified that you do not need to use advanced math. You use just the algebra, which we have learned. Wasn't that interesting?
Yes.
Yeah, it means that then when you make assumptions, then makes the problem much easier. Then you do not need to use the calculus, so many advanced math. You get the variables, which is the most meaningful one, then you just use the basic math to find a solution for a real world problem. Guys, in that video, yes, Rose, does it make sense to you?
Yes.
Isn't that interesting?
Yes.
Nice. Then what kind of problems in that video they were talking about that you can use the math modeling in order to find an answer for it? How many situations they were talking about?
Roller coaster.
What about the roller coaster? For example, you go to 2 different places. For example, imagine that in China, there is a roller coaster, huh?
Yeah.
Also, there is one in Toronto, a roller coaster. You have limited resources in the money, I mean, to spend on buying the tickets. You want to see which one is the most interesting one, which one gives you more thrill, which one is more exciting, the one which is in Shanghai or the one which is in Toronto. Yes? Then you use the math modeling to find a factor which is called the thrilling factor, or the factor which shows which roller coaster is the most exciting one. Then you say, okay, I use the math and I can understand, okay, the one which is in Shanghai is the most interesting one to try it. And that's how, for example, one example of the math modeling. There were also 2 more. What are the others? Can't you remember it? For example, there were 2 other more. They said that, for example, it was very relevant to the fact that right now we are struggling with the coronavirus, the COVID-19, and they said that you can use the math models, a very basic one, which is called SIR, which it's very easy. Then by the math, you can just show how the COVID-19 or coronavirus is gonna spread through the cities then the governments can take some more protective measures then. Can you see? The math model which you use, it has a huge impact on the lives of the others around us. And what was the 3rd option? Rose, Gloria, and Philip? Rose, you cannot remember that?
I I heard something about recycling, but
That's right. You know what is recycling?
I know the meaning, but
Oh,
I know
yeah,
the
yeah, sure. It means that, for example, imagine that the city of Toronto has some problems in terms of how to discard the recycled items as a garbage. Huh? Then you can use the math modeling. I haven't done that myself. I have no idea how is that going to be done, but different that's going to be done. Then you use some math modeling in order to find the best option. And that's in a general term. You have so many strategies. For example, you propose that the recycled items should be recycled by option A, and I say the recycling items should be recycled by option B. Then you can use the math modeling to help the city of Toronto to pick up which option A for recycling the items or option B. Then as a result, you can see that the math modeling, Rose and Philip and Gloria, it is going to connect two things as a bridge. The mathematics which you have learned in high school with the real world problem which we have to find a solution for it. And that's the bridge between these two. Then you use mathematical models, mathematical modeling in order to connect the things which you learned right now in our class with something which is happening right now outside, and some people have some problem with it. You see that? And isn't that exciting?
yes.
Yeah. For example, now you can just use, for example, math modeling. There are some mathematicians right now they're trying to model the spread of COVID-19, the coronavirus in Toronto and all over the world. And the governments, they are relying on their calculations to adopt the policy to say that, for example, you have to do this, you have to do that. And you see, then your high school math is going to play a very important role for people around you. I'm so excited about that. How about you, Rose?
Yes, me too.
Yeah, yeah, awesome. Then also for Philip and Gloria, can you hear me?
Yes.
Yeah? How about Gloria? Gloria?
Yes.
Yeah, then also if you want, still we have some time, you can also let me know whenever you are interested. I can just add you to the team to take part in the math modeling challenge. That's an international competition. Okay?
Okay.
Awesome. And I'm talking to all of you guys, to Rose, Philip, and Gloria. Please make sure that everyone, and especially Rose, that this is in the competition. At the end of the class, go to a folder into our main website. That's from the Schoology. I created a folder last night. This is called Math Modeling Challenge. Yes, Rose? There are two
Yes.
documents in there. Please, and your spare time, when you have some time, to review the PDF documents, okay?
Yes.
And please make sure that to ask me as many questions as you have, okay?
Okay.
Awesome. Then by next week, May the 7th, we formally enter to the competition. It's a 5 days challenge. And during that 5 days, I'm just going to help you all, if you are in the competition, to do the competition. And also, the very last thing, tomorrow also, we see the second part of the video, which we started today for the math modeling challenge and how to use those, I should say, get some preparation strategy for that challenge then. Then as a very last thing, I'm going to check your dates, Rose. If your dates for presentation of the models which we have is between May 7th and May 17th, I'm going to cancel that for you. You will do that after your challenge, huh?
Okay.
Yeah. Then that's pretty much. If you have no question, then we continue with the lesson. Any questions, guys?
No.
No.
No. Guys, let me know who is going to be the next, who is the first one to present the work to me?
Me.
Is it Rose?
Gloria.
Gloria. What is that date, Gloria, for you?
May 4.
Oh, Monday, huh?
Yes.
Very nice. Are you excited for it?
Yes.
Nice. So glad to hear it. Then remember, Gloria,
Yes.
before we do that, you have to also submit your work to me on the Science Club and also prepare your work on the PowerPoint, okay?
Okay.
And try to include as many details as you can because we are going to learn a lot from you, okay?
Okay.
That awesome. Then on that day, you have to share your screen with us that we see your PowerPoint. Is it fine?
Yes.
Fantastic. Are you excited now for it?
Yes.
Fantastic. You are excited too. Awesome. Thanks. Okay, guys. If you have no questions, I'm just gonna put my laptop upside down. We start the lesson right now. Okay, now, what time is it? 10:36. Okay, let's move on. Today we are oh my God, I was supposed to just prepare some, I should say. I posted our course outline. Okay, that's totally fine. I thought that I haven't done that. Okay, guys, today we are getting so close to the day that we are gonna finish the trigonometric ratios and functions. Okay, now let's go on. Okay, yesterday we are very accidentally, when we were trying to solve one question, we ended up to draw the identity by itself. And what did we say? We started with this, that we said that we know that the cosine of alpha plus beta. Guys, can you see that? Do you see the color?
Yes.
Is there too much light or the light is fine?
That's fine.
Okay, awesome. We said that cosine of alpha plus beta was essentially the cosine of alpha, cosine of beta, minus sine alpha, sine beta. That's essentially, that was a thing that we talked about that yesterday. And also the day before yesterday. We quite accidentally noticed that yesterday in one of our problems. Sometimes it happens that the angle alpha and the angle beta in our unit circle, they can be equal in a sense that we say that alpha is equal to beta. Two angles are the same. Then we say that if that thing happens, what's going to happen right now here? We said that it's going to be the cosine of alpha plus beta. Then in a sense, alpha and beta are two angles that they are similar. Then I can just write cosine of alpha plus alpha, right? Or cosine of beta plus beta. In a sense, it means that these two are the same. What's going to happen if I expand this identity? It becomes cosine alpha times the second angle, cosine alpha again, minus sine of the first angle times the sine of the second angle. So far, so good, everyone?
Yes.
Do you see clearly what I have written? I mean, in terms of the color, light, camera.
Yes.
It's fine? Okay. Now, then in a sense, you look at this one and you see, oh, I can just do some more simplification. And the simplification that you think to yourself you can do, it becomes like this. You say that alpha plus alpha becomes what? Becomes cosine of 2 alpha equals to what? Cosine alpha times cosine alpha. It's like to say a times a becomes a squared. Cosine alpha times cosine alpha becomes what? Cosine squared of alpha minus sine alpha times sine alpha becomes sine squared of alpha. Correct? That was the identity we derived it yesterday, and this identity is so crucial to learn. It is one of the most important identities that we are going to work with. Okay. Any questions, guys, so far?
No.
No? Awesome. Now, the thing which I'm going to do right now is that this step is going to be very, I'm going to call this very funny, because this step is going to be very easy, but its impact is going to be huge when we work with the trigonometric function. You know, previously from the things that we have learned, that cosine squared of alpha plus sine squared of alpha becomes how much?
1.
1. So correct. Then now, I'm looking at this term here. I see that cosine is squared, sine is squared, and I remember from the main identity which we have learned, I have also sine is squared, cosine is squared. Then what happens if I want to put, for example, instead of cosine squared of the alpha into this identity, I put its equivalent from this formula. What do I mean? I come here to say cosine of 2 alpha becomes what? Instead of writing cosine 2 alpha, what can I write with this identity? 1 minus sine squared, huh? Because cosine squared becomes, based on this identity, becomes 1 minus sine squared. Yes? Minus the second sine squared from the main equation. Sine squared of alpha. Then now things looks much neater, much easier. Then things now becomes much easier and much neater. Why? Because look at in the previous example, previous identity which we had. In the previous identity, I had cosine and I had sine. I had, in a sense, two things with the different natures. But by using this identity, I reduced it to a formulation which I have only sine to the right side of the identity, which it seems that it's going to be much easier. Then what I'm going to do here, I'm going to make it look much simplifier. I say cosine of 2 alpha equals to what? Equals to 1 minus 2 times of sine squared of alpha. Correct? Everyone is good so far?
Yes.
Good. I have to continue from here. Let me write it back again. What did I have here? I had cosine of 2 alpha equals to 1 minus 2 sine square root of alpha. Okay, that's what I got. The last line which I had written, it was this, that the cosine of 2 alpha equals to 1 minus 2 times of the sine squared of the alpha. Then I'm just gonna arrange it for, I'm gonna derive the sine squared of the alpha. What's gonna happen now? I'm just gonna write sine squared of alpha is gonna be what? I can take this to the other side, becomes plus, take this one to the other side, becomes minus, divide both sides by 2, which is the coefficient of 2 sine. Then becomes what? Then becomes 1 minus cosine of 2 alpha divided by 2. And I'm gonna stop here because this one is gonna be your best friend, guys, for the rest of the term. This identity. This is a very important identity that we are gonna derive. Please write it as I have drawn it here, because this identity is super, super important. Guys, look at this one. The thing which is very interesting for this identity, so far, I find two things which is interesting. The first thing which is interesting is this, that I have the angle which is alpha, but I have expressed it and represented it by the cosine of a 2 times of the angle, 2 alpha. This is very important to notice. You have alpha on the left, and you have 2 alpha on the right. And essentially, you are representing the sine squared of that angle with an expression which has power 1. There are two things very interesting of this identity. Please take a note of these two things, because we are going to go back to this and apply them over and over again. These two things which I told you, it's very, very important. The first thing is that, guys, I have the alpha on the left, but I have 2 alpha on the right. Okay? The second thing is that on the left, I have the power 2, but on the right, I have power of the trigonometric ratio 1. This is also very important, and they use that property in a case they call that power reduction technique. This is one of the most beautiful things which you are going to do this week. Then please take care of these two interesting facts. Okay, and now I'm done with the sine squared of the alpha, and I'm going to continue with something new. Any questions, guys, so far?
No.
No, everything is fine.
Yes.
How about Gloria and Philip?
Yes.
And Philip?
Yes.
Awesome. Okay, now, this is going to be our equation number 1. The second equation, to drive it, I'm going to go back again to this one. I'm going to start again by the same thing. I'm going to start again by the cosine. What did I have? I had cosine of 2 alpha was equal to cosine squared of the alpha minus sine squared of the alpha. That was a thing which I talked about that. That's what we derived. But at the same time, we saw that, okay, we had this identity valid, that we knew that the sine squared of alpha plus cosine squared of alpha, it's going to become 1. Previously, on the previous strategy which we had, we came here, we said that, okay, I'm going to rewrite this identity by putting 1 minus sine squared of the alpha for cosine squared of the alpha. then I expressed everything on the right side of my equation in terms of the sine squared of that angle, right? And now, the other thing which I'm going to do is this, is the fact that I'm just coming to work here and say, okay, now I'm going to start from the same equation, but instead I'm going to put something for the sine squared of the alpha. What it means, I'm just going to write cosine of 2 alpha. It's becoming cosine squared of the alpha, the same thing, minus, but for the sine squared of the alpha, I use this identity to express sine squared in terms of the cosine, which becomes 1 minus cosine squared of alpha. I didn't do anything except for the sine squared of the alpha into the main identity. I substituted with this expression that the sine squared becomes 1 minus cosine squared. Then I'm just going to make it look a little bit neater. Then what's going to happen? It becomes cosine of 2 alpha becomes 1. Sorry, I had to, let me write it this one first. Becomes 1, becomes 2, becomes 2 times cosine squared of alpha minus 1, correct? Then as a result, if you want to express the cosine squared of the alpha, you write it like that. You say that cosine squared of the alpha becomes what? Becomes, you take it to the other side. Okay, you take it to the other side, becomes 1 plus cosine of 2 alpha divided by 2, which is going to be the second identity that we are just going to stick to that today. Let me highlight this. Now I have equation number 1, and I have equation 2. I followed the same thing, and I got the same strategy, and I got a different expression for this one, for the cosine of 2 alpha. Guys, any question, how did I derive this formula?
No.
Everyone is okay?
Yes.
Awesome. Thank you. And now, guys, again, I repeat the thing which I said previously. Two important, interesting thing about this equation. And this is about the fact. The first one is that you see the alpha here, but you see 2 alpha there. That's the connection, that one angle is connected to twice of it on the other side. That's one important thing. The other thing which is important is that you see the left side, the cosine has a power 2, but the right side, cosine, has a power 1. These two things are two important property of this stuff. Then we are going to expand on these two properties in 2 minutes in order to drive some interesting fact about these two equations. Then, guys, any questions so far?
No.
No? Awesome. Okay, Gloria?
Yes.
Okay, can you please tell me two important property of these identities? Give me one. And I ask also Philip the other one. Gloria?
Yes.
Yeah. Do you want Philip to start and you tell me the second one, Philip?
Yes.
Philip? Philip. Philip. Gloria.
Yes.
Okay, tell me one interesting property about either of these two properties. I said two, you tell me one. And I asked Rose the other one, huh?
First one.
Yes. Philip, do you want to say something?
I'm still.
Tell me one property, interesting property of these two identities. How about Rose? Maybe Rose says something, then you continue with it. Rose, do you know some property about them which is going to be interesting? Rose?
Yes.
Do you want to say one interesting property about this equation?
Is it the two equation on the paper?
That's right.
Sine squared r alpha equal to 1 minus cosine 2 alpha over 2.
That's right. What is interesting about this identity? Is it the fact that this one you have alpha, the other side you have 2 alpha? And also the second interesting property is that for this one you have power 2, but to the other side you have power 1, right?
Yes.
Yes, everyone?
Yes.
Okay. Now, I'm just going to move on to do some examples. Okay, now, I'm just going to give one example for you. And why do we need these identities? Imagine that we are talking about the functions, then we should talk about functions at the same time. I'm going to say, imagine that I have a function, the function is called f of x. Is going to be 3 times sine to the power 4 of the x. Just give me 1 second at the back in a second. Okay, let me write it on the other side of the paper because f of x 3 sine to the power 4 of the x. Okay, now everyone please listen to this very carefully. This is a very important example. Please make sure that you learn step by step, otherwise you miss all the materials together. Okay, the thing which I'm going to do here is that this function which I have here right in front of me It's a function, as you can see, it's only one term because I have only the sine to the power 4 of the x. I have only sine to the power 4 of the x, and 3 is multiplied to that. The plan is that. The problem is that sometimes in the math, I want to reduce the power 4 of my identity. And I say, okay, I'm not going to care about the power 4. I want to decompose my function into the linear combinations of the terms which they have power 1. I'm going to do that now. I'm going to take some steps to do that. Please you write these steps because you're going to need that a lot in future. The first thing is that, guys, it's a kind of a magic now because you will see that my function is expressed into only one term, but I'm going to expand it into many terms. It's a kind of a magic. Don't be surprised if you see that. It's a very, very, very interesting thing to do. The first thing which I do, I take a look at the sine squared of the x. Sorry, sine to the power 4 of the x. I'm going to do what? I'm going to rewrite it as 3 to these identities which we derived, guys, sine squared of the alpha and cosine squared of the alpha, all of them is expressed in terms of the power 2. Then it becomes a kind of a roadmap for you. Whatever you do, you have to express your function, the trigonometric part of your function, as either the sine squared of the alpha or cosine squared of the alpha. Then they become the building block, the fundamental component of your functions. And as a result, sine to the power 4 of the x, I can write it as this: sine to the power 2 of x, which it goes to power 2. Then I should be very happy now because at the same time, I was able to reshape, reconfigure sine to the power 4 of the x in terms of the sine to the power 2 of the x, which I need to see to the power 2. And at the same time, these two are equivalent because 2 to the power 2 becomes 4, then becomes sine to the power 4 of the x. Then it means that, and I have 3 here. It means that I rebuilt the function which represents the same function, but this one is going to be in that representation. Okay, now, then this one. I'm at this stage now. Okay, what's going to happen now? I see sine squared of the x. I take a look back at the notes which I have. Sine squared of the x. Sine squared of the x. I derive the formula for it now that it's equivalent to 1 minus cosine of double of the x, cosine of the x divided by 2. I remember this identity. I call that equation number 1. I'm going to rewrite it here. I'm going to use this one there. I'm going to write, then it becomes equal to 3 Now, instead of writing sine squared of the x, I know sine squared of the x as I derived it today, and it was very easy. It was very easy to derive this. Then the sine squared of the x becomes 1 minus cosine of 2x divided by 2. And that was the reason I called to learn this interesting property that if you have x here, or if you have alpha here, on the other side, you have 2 times of the same argument. Then as a result, I'm using this equation, write it here. It becomes 1 minus cosine of 2x. That's why I emphasize that's an interesting property. Divided by 2. However, I see outside power 2 is waiting. I don't make it to wait more. I put the power 2 here. Now, what's going to happen now? The most reasonable thing that you can think of is that, okay, you take a look. You say, I have 3 here. Oh, I can't do anything with it. I have an expression inside the parentheses, but all of them is going to the power 2. Then the best thing to do is that to work with the power 2. Then what's going to happen then? I take 2 to the power 2 because you know that if power 2 is for a ratio, the numerator goes to the power 2, the denominator goes to power 2. I take the denominator to power 2 first, becomes 2 to the power 2 becomes 4, and I take it out. Then becomes 3 divided by 4 times what? Times 1 minus cosine of 2x to the power 2, which essentially, I'm going to simplify that further, becomes what? Becomes 3 divided by 4, and I have power 2. Expand the power 2. Then 1 to the power 2 becomes 1. I have minus 2 times cosine of 2x plus this term to the power 2 itself becomes cosine squared of 2x. You see this, guys?
Yes.
Yeah? Any questions so far?
No.
No. Awesome. Then I have 2 options to do. I say, okay, my f of x was 3 times sine to the power 4 of the x. I can rewrite it as 3 over 4, 1 minus cosine of 2x plus cosine squared of 2x, and I say I'm done. Or I say, okay, wait a minute. I want to represent everything with the power 1. And I come here, I see, oh my God, I have one more term. This is cosine squared of 2x. Cosine squared of 2x. Again, it has a power 2. Then I knew that the cosine squared of alpha, based on the equation number 2, which I learned, can be written as 1 plus cosine of double of the angle divided by 2. That's why I say these 2 equations, they are the most important equations for power reduction. And please take these 2 ones as your best friends. Sine squared of alpha and cosine squared of the alpha. These are very important equations. Be good friends with them. Then as a result, I'm just going to rewrite this. I say it's going to be 3 over 4. I have 1 minus 2 times of cosine of 2x, but plus, instead of writing cosine squared of 2x, I'm going to use this identity to rewrite it as what? Plus I have 2. Please take a look at your equation number 2. Then I have 2 here. And I have 1 plus cosine of double of the x. I had x here. I had here 2x, guys. Please take a look there. This is very important, which I used to always make a mistake myself when I was going at the high school. I was at your age. Look at this argument. This argument is 2x itself. Then when you want to rewrite it by base equation number 2, you have to double it. Becomes how much? Cosine of double of the 2x becomes 2 times 2x becomes 4x. Right? Then we are done. Then as a result, I can say the magic right now here. I hope that you see the magic which I'm going to write. Then you can say 3, the functions which you had, which it was what? 3 sine to the power 4x should be equal to 3 over 4 of 1 minus 2 times of cosine of 2x plus 1 plus cosine of 4x divided by 2. And now we are done. And you see the guys, you see the magic now. We started with the function f of x, which it was 3 times sine to the power 4 of the x. A function only and only with one single term. But you see that at the end, what did I do? At the end, I came here and I expanded. The function is exploded to be expressed in that way. One function with one term is essentially the same thing with which you have 1, 2, and 3 terms. You see, all of them is expanded. And the brilliant thing about that is that look at the right side. The left side, I had sine to the power 4 of the x. But at the right side, I have cosine of 2x. What is the power of that term? 1. I have cosine of 4x. What is the power of that term?
1.
1. That's so true. Then you will see that you reduced. You did 2 things essentially now. 2 brilliant and exciting things. The first exciting thing which you did was this. You, first of all, with a function of one term, you decompose it into many terms. 2, with the function which it had a power which was not 1, it was 4, you have now on the right side all terms power 1. And that's why I'm telling you these 2 properties are the most exciting properties which you can learn in the trigonometric function. Because at this stage of the trigonometry, we are going to do things which is more fun and more exciting to do. You expand the function into many terms, and that's quite a thing. Okay. Any question?
No.
No question, guys? Philip, Gloria?
No.
No? Okay. If you have no questions, guys, then it's a good time to take a break. It's now 12. Let's cheat today. Imagine now this is 12:15. I go 2 minutes ahead. This is now 12:13. Come back by 12:30 then. Take 16 minutes break. Come back 12:30. We continue from there. Okay. See you guys later then. Hello. Hello, guys. Are you back?
Yes.
Awesome. Okay, now, any questions of the examples that we had? No questions?
No.
Then now, the thing which you want to do, I have one question for you that you can also practice it. Okay, I'm going to give you this example that imagine that we have a function and the function is given as this. Everyone is back? Gloria, Philip?
Yes.
Okay, everyone is back. Okay, I'm going to give you a function which is going to be 4 times of cosine squared of the 5x plus 10 times of cosine to the power 4 of 3x. Okay, I think that's a very good example to start with. Guys, please take a look at this function. This function has 2 terms. We have term a I have this one here as term A, and this one here is as term B. Term A and term B. Okay, you see that f of x is a function, is a trigonometric function, which it has 2 terms. Term A, which is 4 times of cosine squared of 5x. The other one is that plus 10 times of cosine to the power 4 of 3x. Term A and term B. They are a linear combination to make the function f of x. And now the thing which I want to ask you, please, it takes some time. To spend some time, it doesn't be done in 1 or 2 minutes. To reduce the powers of 2 and 4 for term A and term B, then decompose f of x into a linear combination of all the functions which has power 1. That is going to be exactly as what I did for this example. If you learned the previous example which I did, you can redo this again for this term, but here you have 2 terms to start by term 1, then go to term B, then add them together. Does it make sense to everyone?
Yes.
Yeah? Please then take a couple of minutes and remember, you need these 2 identities very much. Equation number 1 and equation number 2. You need these 2 one at any step that you're just going to do working. Just have them handy and continue with that one. Okay. I'm going to give this one here and this one here in case if you need this to see that. That's the example which we are going to do. And let me know if you have any questions while you do that. Gloria and Farron, Philip, are you working on it?
Yes.
Awesome. Okay. Guys, anybody's done or no? You need more time?
Not yet.
Not yet. Okay. Felipe and Gloria, are you done? Okay, Rose, are you done?
Almost.
Almost, great. How about Felipe and Gloria?
Not yet.
Philip?
Almost.
Almost, great. Is it good that you have 2 minutes more time, guys, than I do it myself? That you can work, check your work?
Yes.
Awesome, good. Okay, in the meantime, let me just do the attendance for the class. Attendance. Okay. finish attendance and okay. Okay, shall I start? Are you done or you need some more time?
Yes.
You need time? Rose, you mean that you need more time?
Uh, I think I'm done.
Okay, how about you, Philip?
I'm done.
Okay, Gloria?
I'm done too.
Okay. Okay, let's go, guys. I'm gonna start working on this, and you please help me to just go along, and just maybe I go wrong. I need your help to let me just finish it corrected. As I said, I divided both terms, the function in two terms, term A, term B. I'm gonna do separately for each term, expanded based on using the power reduction techniques. Then I add them together based on these coefficients which they have. I'm not gonna use coefficient 10 for term B. I'm not gonna use coefficient 4 for term A. And at the end, I add them together. I'm then start by the term B, which is cosine to the power 4 of the 3x, which is the more complex one. Then essentially I can, guys, you can see this color, the light is good.
Yes.
Yeah. Then I write it as a cosine to the power 4 of 3x. I can write it as the cosine to the power 2 of 3x. It goes to power 2. And I know that the cosine squared of 3x, I use these identities, then I can just do what? I can expand it into a term which it has two properties. One is that angle is doubled, and the second property is that the power is reduced by 1. If the power is 2 here, here it's power reduced by 1. That's why they call that power reduction technique. Then what I'm going to do here, I just come right over here and I write my formula like this. And I write it like this. I should say the parenthesis here. It becomes what? Becomes 1 plus cosine of what? That's the question now. Double of this angle. This is 3x. Then you need to multiply it by 2 to write it here. Becomes 6x. Divided by what? By 2. And I don't forget that I have still the square of this term, which I have to take it. Which essentially I can write it like that. I take the 2 outside, becomes 1 over 4 of 1 plus cosine of 6x to the power 2. So far, so good, everyone?
Yes.
And as a result,
Yes.
awesome. I'm going to expand this. I don't forget I have to put 1 over 4 at the back. Then what do I get? I get 1 plus 2 times of cosine of 6x plus square root of this term plus cosine squared of 6x. Some of you may wonder, okay, I did enough after decomposition. I may stop there, but the problem is that I have this term here, which it has the power 2 still inside. Then as a result, you see that you cannot stop here. You can continue further, still you can decompose this expression. Then I mean what you can do, you can still write 1 over 4. You write these terms 1 plus 2 times of cosine of 6x plus the other term is cosine squared of 6x. You can again use this identity, equation number 2, that you reduce the power from 2 to 1. You see, it's a successive, I should say, application of this identity. Becomes 1 plus cosine of what? Anybody knows? It should be double of the previous term. Your cosine squared of 6x. When you use equation number to reduce the power, you see that the angle becomes twice of the thing which you have. Then it becomes how much? 12x divided by 2. Any question, guys, for the term b, which I expanded?
No.
How about Philip and Gloria?
No.
No? Then, guys, you see that you start with the term which it had the power 4. You reduce all powers to 1 by successively using, I should say, equation number 2. And more importantly, you see that from the angle of 3x, you went to 6x, and at the end, you ended up with the 12x. You see, it's twice at every stage. Huh? Isn't that nice? Okay, that's for term A. For term A, which is, I can write it here, it is for what? It is for cosine to the power 4 of 3x. Term A is very easy because it's the simple once using of the formula for once. Then as a result, what I'm going to do, I'm coming here to rewrite the whole expression to write the f of x itself. Then I can write f of x should be equal to what? 4 times of what? Cosine squared of, what is that? Cosine squared of the 5x. Becomes 1 plus cosine of double angle. Double angle 5x becomes how much?
10x.
That's right, 10x divided by 2. And plus term b. What is my term b? Is 10 times of cosine to the power 4. Cosine to the power 4, we got it here. Then it becomes plus 10 divided by the 4 of this expression. Which is 1 plus 2 times of cosine of 6x plus 1 plus cosine of 12x divided by 2. And now we are done on only one single page. We are able to finish this exercise. Any questions, guys? Does it make sense to all what happened?
Yes.
To Philip and Gloria also?
Yes.
Oh, Philip is gone, huh? Philip leaves too early these days. Okay, guys, then in order to wrap up, you will see that these functions, you started with one simple function and you decompose that function to a linear combination of a trigonometric function in which the power of each trigonometric ratio is simply 1. These two functions are essentially the same thing, right? And that was a plan which we did. Any questions? If no, Gloria, did you get the same answer as I got?
Yeah.
How about you, Rose?
Yes.
You got the same answer?
Yes.
Okay. Now, if you have no questions, we are going to do something right now more. And the thing which we are going to do is this, that we plan to plot these two functions by Desmos, because if these two functions at this stage they are equivalent, it means that they have to have the same plot, the same graph. Then please plot these two functions on Desmos. Once plot this one with this and plot this one also at the same page. Then you see that if these two plots are exactly matching each other, if that's the case, it means that we were able to decompose these functions properly and these functions are equivalent then. Okay, that's going to be the task. Please now plot these two functions, then you have to share your screen to, as I think we have almost 15 minutes left, then you share your screen and we see what have you plotted. Okay?
Okay.
Awesome. And I'm going to do the same thing here myself. Desmos. Function looks a little crazy. Okay, who's done plotting? Rose and Gloria? How's your plotting going on?
I haven't done.
Yet, huh? No problem.
Somebody go ahead.
Who was that? Too much plotting, huh? Okay. Are you done, Rose?
Not yet.
Okay. How about Gloria?
Not yet.
Okay, guys. Let me share my screen. Please see what have I plotted. Okay. Please, everyone, stop working and see the plot which I have made. Let me share my screen. Okay, now. Okay, everyone sees my screen?
Yes.
Okay, guys, look at that. The first function which I have. The first function was f of x 4 times cosine square root of 5x plus 10 times cosine. And remember, if you put cosine to the power 4 of the x, it's not going to be plotted. That's why you have to just write the 2, then put it to the power 2 then. Okay? Becomes then cosine to the power 4 of 3x. Did you have that same problem?
Yes.
Yeah? Then because you have to just put power 2, because it's power 2 only supported, and plus and power to the power, let's say, minus 1. For example, for any higher powers, you have to let the strategy which we had. You write it based on the power 2, then make up the whole power like that. Yes, Rose, you learn it? You got it?
Yes.
Awesome. Look at that. That's the first function which we started with in order to decompose it. Let's see, what do we have? This is the plot. You see that? And now, look at this, the other plot. This is the plot, the second part is the plot for the function which we decomposed, the second line. You see the second line?
Yes.
It's the decomposition which we made. You see that all cosine terms, they have the exponents 1 cosine 10x, cosine 6x, and cosine 12x. All of them, their power have been reduced to 1. You see that when I plot it, it exactly matches the same plot. You see that both of them are on top of each other. You see that?
Yes.
That's right. Okay. Then as a result, look at that. For example, this one is this plot. I plot the other one. You see that this is on top of the other ones. You see how pretty is that?
Yes.
Then as a result, you will see that when you started with this function, and when you decompose this function into this function, which you have reduced its power to 1, then you will see that, very interestingly, that these two functions are equivalent. They represent the same plot and the same representation on the plane. Then the lesson that we learned today is very interesting because we can decompose the functions, just trigonometric function, into the sum, a linear sum of the terms which they have their powers reduced to 1. And at the end, they should be equivalent. They represent the same thing on the plane x and y, right? Any question, Rose and Gloria?
No.
No? Okay. Then guys, if you have no question, I have to I'm gonna end the session today, but remember, tomorrow you need a new access code for the Zoom. I'm gonna provide you the link tonight. Then when you log into the Zoom tomorrow, you need a new password. Okay?
Okay.
Awesome. Then thank you very much. Then if you have no question, then I will see you all tomorrow. Let me stop sharing my screen. Okay. Thanks, Gloria. Thanks, Rose. Have a good day. See you all tomorrow then.
Okay.
See
Bye.
you.
Bye, everyone. See you tomorrow. Rose,
Yes.
are you excited for the math challenge?
Yes, sure.
Yeah, that's the exciting thing, huh? Because you see how the math which you have learned in high school can impact people's life around you in real life. And it's very exciting to see that.
Yes, me too.
That's right. Then tomorrow, I prepare some materials for you in the class that we can warm up for the challenge next week then.
Okay.
Awesome. Then have a nice day, Rose. I see you tomorrow. Take care.
Okay.
Thank
Bye.
you. Bye. Bye-bye, Rose.